Pergi. Pergi kecil. Dia hilang. Okay, so we have finished with the formula, how to calculate the power when we have the current, or how to calculate the power when we have the voltage. Okay, so we move into the example. Okay, so example 1. Okay, so we go into the example 1. I think this example is really very straightforward. Okay, so in this example, okay, an antenna has an impedance of 40 ohm. So they give you the impedance. So this impedance is actually equal to R. Okay, you have R here. Okay, when you have impedance here, you have the R. Okay. Again, an unmodulated AM signal produce a current of 4.8 ampere. So the keywords here is actually unmodulated. So meaning that is actually IT or IC. IC, right? Okay. So you know that the keyword is unmodulated. So this is actually the value of the IC. Okay, the value of the IC. And then you have the modulation is 90%. So that is the modulation index. So 90% converted into the index, you will get 0.9. Okay, you get 0.9 because this is 90 over 100. Right, so 0.9. So it asks you to calculate the carrier power. So meaning that this is the carrier power. So this is the PC. Okay, and then the total power, which is the PT, and the sideband power, which is the PSV, sideband power. Because here they just mentioned the sideband, so it can be actually referring to the both sideband. So actually referring to the upper sideband and the lower sideband. Okay, the upper sideband and the lower sideband. Okay, so the first one, carrier power, because you already know what is the IC. Okay, you already know what is the IC, and then you already know what is the R, so we substitute into the PC. Okay, so we remember that when we have the current, we use the I squared R, right? Because here we have the current, we don't have the voltage here, we have the current, so we just simply use the equations of the I squared R. Okay, I squared R, so we get the answer there. So the total power, okay, because now we already have the PC here, and we have the modulation index, so we can use the P total here. P total here is equal to PC plus 1 m squared over 2. So just substitute, you get that answer. So this is like, if you know on how to identify what are the important parameters and how to use that parameters into the equation, so you know what is the equation that you can use. Okay. And then the sideband, okay, the sideband. So the sideband meaning here is the sideband. So how to calculate the sideband? Okay, so how to calculate the sideband? Okay, how to calculate the sideband? Okay, you can, here in this equation is because the total side, okay, the total power is actually PC plus 2 sideband, right? Power of USBs, maybe like this. Okay, so you can use P USB is equal to PT minus PC, right? PT minus PT, and you divide it by 2, right? You divide it by 2, and you get the power sideband over there. Okay, so they use that equation. They can use that equation to get the sideband. So just substitute, then you get the answer. So the sideband power also can be calculated using m squared, right? So maybe PUSB, remember that is equal to m squared over 4 PC. You can also use that one, PUSB, m squared over 4 PC. So because you already have the modulation index, you have the PC, you can calculate whatever an equation. So these two should be the same answer. That two should be the same answer. Okay, so that is the example 1, example 2 here. Okay, in this example 2 here, okay, in example 2, so they give you the total power here, PT. Okay, PT is 100, the total PT. Okay, okay, so here they give you PT. Okay, they give you this is total power. Okay, so that is PT. Okay, we know this is PT, and they ask you to calculate M. Okay, what is M? If each of the sideband contains 75 watts, so this is sideband, right? So they give you the value of the sideband. Okay, what you have here? You have PT, you have PUSB, right? You have PT and you have PUSB. So meaning that you can use the equations of the PT and PUSB, right? And just substitute that one. Okay, you have the PT here, you have the PUSB here. Okay, PT and PUSB. You rearrange that one, you will get the PC, right? You get the PC and you can get the M. Or you can also use PUSB, right, is equal to M squared, right? Because but you have this PT, you just have that PT, so you don't M squared over 4 PC. In this case, you only have one equation. What is the PC? Right, they use this one. Okay, they use this one. USB 75. They rearrange this one. Okay, yeah. So rearrange that one, you will get the M. Okay, you get the M. So first you have to identify what are the parameters that get given in the question, and you have to think on how to play around with the equation to get the answer. Okay. So example 3 also here. Here they ask you to find the carrier. Determine the power of the carrier. Okay, so meaning this is PC. What is the PC? For each of the side and power of the sideband. So they also ask you to find the power of the sideband. The one that they give you, the information that give you is the modulation index. M, so here is M is equal to 0.8, and the total power PT. Okay, so you have this PT, you have the M, and they ask you the carrier, So you can use this equation, right? Because you already have the M, you also have the PT. Rearrange the one, you will get the PC. Once you get the PC, substitute into this equation, you will get the lower sideband and upper sideband, each of the sideband. Okay, that one is very straightforward, right? Okay, you can follow until now. Okay. Okay. After we know on how to calculate the power, now we will move into how to save the power. Okay. Previously, you want to calculate, you just want to calculate what is the PC, what is the lower sideband power, upper sideband power, the total power, if either voltage is given or current is given. Okay, but now we want to save the power. Why we want to save the power? Okay, we can see from this spectrum, okay, we can see from this spectrum, okay, we can see the relation, right? We can see the relation that, let's say, okay, we make it like simple, m is equal to 1. Let's say the modulation index is equal to 1. What we can see? We will see that at the carrier we have the PC. At the lower sideband we will have PC over 4, right? And at the upper sideband also PC over 4, right? So meaning that here, the total power actually is dependent on your carrier, but the carrier doesn't have the information. The information is carried by the lower sideband and upper sideband. Why? Is because if you look at into that equation there, the modulation index is actually represented by the lower sideband and the upper sideband. So that modulation index actually carrying the information, because you modulate the signal based on the voltage, right? So only lower sideband or upper sideband is having the information, while the carrier, there is no information. The carrier is just the carrier, okay? So meaning that we waste our power into the carrier, but the carrier doesn't carry any information, okay? Also, if you look at into the bandwidth, it will create two sidebands, and the lower sideband and upper sideband actually having the same information, okay? So what are the wasted components here is, first is actually the power, because we put more power on the carrier, but the carrier doesn't have the information, okay? And it also utilize bandwidth, right? Because now lower sideband and upper sideband having the same information, but they occupy that bandwidth, okay? They occupy that bandwidth, so we waste our bandwidth for carrying the same information, okay? Redundant information here. So what happened? To save the power and the bandwidth, okay? So people introduce double sideband suppressed carrier, double sideband full carrier, single sideband full carrier, and single sideband suppressed carrier. So the previous one, this one is known as the double sideband full carrier. Double sideband full carrier, meaning that you have the carrier, you also have the two sideband, okay? So that is meaning of DSBFC, okay? DSBFC here, that's meaning of the double sideband full carrier. So they introduced double sideband suppressed carrier. So the words here is they suppress the carrier. The carrier is there, but they suppress so that they don't waste power on that. And or they have the one sideband with the carrier, or they only have one sideband. They suppress the carrier and another sideband, okay? So how does it looks like, okay? So we can see that, okay, here double sideband full carrier, we have the signal at the lower sideband, the carrier and the upper sideband. So we have the bandwidth 2 FM here, and the power we total up all of those, okay? And then double sideband suppressed carrier, okay, they suppress the carrier, so the carrier isn't there, okay? It's there, but they just suppress, okay? So meaning that in the modulation, they use the carrier to modulate. They don't eliminate the carrier, but just to transmit, they suppress that carrier. So they still have the two sideband. They still have the two sideband. So meaning the bandwidth is still 2 FM. The bandwidth still FM. But the total power now, we just have the lower sideband and the upper sideband. Okay. So meaning that what are the power that we save is the one that we suppress, which is the PC now. So we want to calculate how much power that we save when we suppress the carrier is just the total save, okay, the power save over this double sideband full carrier over the conventional one, double sideband carrier, multiply with 100. So we can calculate how much power that we can save when we use double sideband suppressed carrier. Same thing with the single sideband full carrier. So in this case, we suppress, okay, we suppress just one sideband, okay. That when we suppress one sideband, so we can save the bandwidth, and we can also save the power. So the power that we save on the one that suppressed here, we still have the carrier and also the sideband. Then the power save is just the power save over the double sideband full carrier, okay. And the single sideband suppress carrier, okay, here we suppress two, so we can save the bandwidth, we also can save the power, so the power save is these two, okay, and then we can calculate through that, okay. So this one is just even though both the formula is given here, but this formula is coming from the understanding of how this double sideband is represented. So if you know how that one is represented, you can draw the spectrum, you can calculate the bandwidth, you also can calculate the power save, the percentage of the power save. So if you understand how these types of power is constructed, you don't have to memorize that. You can generate the equations based on this understanding. So it's really important for you to understand what does meaning by the SSBFC, double sideband SC, suppress carrier, suppress sideband. Okay, so this is the representations in terms of the waveform, into the spectrum. So every time when we look at into the we will look at into both sides, the frequency spectrum and also the time domain, okay, in terms of the waveform and also in terms of the spectrum, okay. So the first one, okay, this is the standard one where we have the this envelope, okay. What happened when we suppress the carrier? So why does it looks like this, okay? So previously we go into how the mathematical derivations of that, but we don't want to go into that mathematical expression. We just want to draw to can get the understanding from understanding on how that one is constructed, okay. So we know that, okay, right? We know that when we want to construct the envelope, we will draw this one, the reference lines of the BC, right? And then we know that this is BM. So this is actually your modulating BM, right? BMT. So that is why you get this waveform. Okay, this is double sideband full carrier. Okay, what happens if you suppress the carrier? You still have that double sideband, but you suppress the carrier. So meaning that you actually eliminating this. You eliminating this. You eliminate this. The carrier now. You don't have this carrier. Right, you don't have the carrier, meaning that you combine. So you combine actually, because you eliminating the carrier. So you eliminate this carrier, eliminate the carrier. What happens is you combine that. So meaning that you will have this. Right, because the carrier isn't there, so this is actually your VM, right? And the one inside this one is actually the lower sideband and the upper sideband. Okay, this is actually lower sideband plus upper sideband. Okay, and this is your VM. So it will go into this original zero reference line. Previously, you have this VC as the reference line. So that is why, when you look at into this, okay, look at into this, you will get this waveform. because you eliminate the carrier. Previously the carrier here is the reference line. You eliminate that, so that combine that positive and the negative one, you will get this. Okay, that is why the waveform is like that. While for the single sideband suppressed carrier, you only have one frequency. Okay, here you still have these two frequency, but here you only have one frequency and one amplitude. That is why you only have the sinusoidal wave here. This sinusoidal, the standard sinusoidal waveform, where you only have one frequency and one voltage. Okay, one frequency and the one voltage. So that is how the signal is represented in the time domain. Okay, then we move into this. Okay, we move into this example. Okay, we go directly into the answer here. Okay. Okay. So in this case, they mention that they give you double sideband full carrier with peak unmodulated carrier. So that is the VC here. There is a VC there. They give you the frequency of the carrier, the load resistor. Okay, this is R. Okay, and then modulating carrier, and then the modulation index. So you have to calculate the power. Okay, so if you want to calculate the power, okay, it depends on the one that is given. So the power of the carrier upper and lower sideband. So the given one is the voltage. Okay, R resistor and M. So you want to calculate the power of the carrier, the PC. Simply use this equation, substitute that one, you will get the answer. Okay, and then for the lower and upper sideband, same thing. Okay, you know what is the formula. You know what is the formula. You substitute into that, you will get the answer. Okay, so I think this is just the mathematical skill. So you don't have any problem to substitute that one. Okay, the total power also the same. Just use the total power formula, this one. Substitute, you get the answer. Okay. And the bandwidth, we know double sideband full carrier is actually 2 FM. So just substitute that one, you will get the answer. Okay, right? And then to draw the frequency, okay, same with the voltage spectrum, you have to label, right? Label what is the value of the PC, what is the value of POSB. Don't leave it like this. Okay, don't leave it like a general formula. You have to put that value in your spectrum. Okay, same thing with this here. Don't leave it like FC minus FM. You need to put what is the value there. Okay, what is the value there? Okay. Okay, so okay, right? That one is very straightforward, right? You should know what is the formula and then substitute into that formula. Okay, and then now this the second question is the same given values. Determine question. The same question, but in this case, they want you to investigate what happens if you have suppressed carrier, if you have single sideband full carrier and suppressed carrier single sideband. Okay, and calculate the power saved. Okay, so for the double sideband suppressed carrier, so double sideband suppressed carrier, so you don't have the PC here, no PC. Okay, no PC, double sideband, so just total up that one. Okay, and then because you still that here is double sideband, so you still have the bandwidth is equal to FM. And then to draw the spectrum, so you suppress the carrier there. So meaning that you still have the carrier there, but you just suppress. So usually it's represented by this dot. So you need to draw it that dot. What is the value? Okay. Okay, the total power. So yeah. So that is okay. Just put it there. Okay, the total power 125. So that is the planning. And then the power save. So meaning that the one that you save is actually PC. You substitute into that equation, you can see that how much you save here. So you save it 66%. So very high, right? When meaning that when you have double sideband, you just suppress the carrier, you get 66% saving. Okay, 66% saving. Okay, so for the single sideband full carrier, so you still have the carrier there, so you can calculate from here the total power. You don't have just one sideband, right? You don't have, so P lower sideband here, you don't have that one. So you don't have that one, so this is the one that you save. So this is the one that you save, right? So substitute that one, okay. So meaning that here, if you just save, or if you just suppress one sideband, you only save like 16%. In terms of M is equal to 1, if the modulation index is equal to 1, just 16%. But previously, if you suppress the carrier, you can save 67%. So see how much you can save. Okay, if you suppress both carrier and one sideband, you see the percentage that you can save is until 83%. So you can see that you can save the power if you introduce the suppressed carrier or suppressed sideband. So yeah, so that's all for today. We finish with this AM. Okay, we finish with the AM.